Welcome to Yaka Digital Network. I'm glad you're here. Have you ever watched a boda bounce down a heavily potholed dirt road and wondered, how does it not just shake itself to pieces? There are hundreds of individual metal parts vibrating violently against each other, yet the machine stays whole. The answer comes down to a core concept in engineering called joining. Joining is the process of taking physically separate components and connecting them to form a single working assembly. If we look at this animated diagram of a motorcycle separating into its individual parts, we see how engineers organize every connection into two strict categories based on lifespan. First, we have permanent joints, like the solid metal frame. Second, we have temporary joints, like the wheels and engine casing. A machine's ability to survive that bumpy road, while still being repairable when it breaks down, depends entirely on choosing the correct joining category for each specific part's function. Let's look at those temporary or demountable joints first. These are connections engineered specifically to be assembled and taken apart over and over again, without causing any damage to the components themselves. The most common way to do this is with threaded fasteners. Think of the heavy steel bolts and nuts holding a motorcycle wheel in place. They lock the wheel securely, but a mechanic can easily remove them when it's time to change a flat tire. Here we see an animated diagram of a 2D cross-section showing how a steel bolt and nut actually hold together. As you slide the nut on, the physical shape of the bolt's ridges traps the opposing ridges of the nut. We call this mechanical interlocking. You're using the physical strength and geometry of one piece of metal to prevent the other piece from sliding away. If we zoom in closely on where those metal threads touch, you'll notice something important. The atoms of the bolt and the atoms of the nut never actually mix. The structure of each metal remains completely separate, which is why you can simply unscrew them later. When deciding on a joint, always check if the part needs to come off later. If it requires cleaning or repair, the only logical choice is a demountable joint, like a nut and bolt. Temporary joints intentionally sacrifice absolute maximum strength in exchange for giving you access to the machine exactly when you need it. But what about the structural frame of the motorcycle? You never want the frame to come apart. For this, we need permanent or non-demountable joints, connections designed to last the entire lifespan of the product. For joining thick steel structures, the ultimate permanent method is arc welding. It uses electricity to generate an intense arc of heat, melting both the parent metal and a filler rod to create the strongest possible bond. This animated diagram shows how heat turns solid metal into a unified mix. When we apply that intense arc of heat, the tiny particles that make up the steel start to shake so violently that they break out of their organized rows. Once they break free, the particles from the two separate pieces of steel and the filler rod mingle across the boundary line. Then, as the metal cools, they settle down and lock into a single unified structure. The physical boundary between the parts completely disappears. Because the separate pieces of metal literally melt into one continuous solid object, a properly executed weld is often stronger than the surrounding steel itself. Permanent joints like fusion welding give you absolute structural integrity, but the trade-off is permanent. You can never take those parts apart again without destroying them. If welding is so strong, why don't we use it for every single permanent joint? Well, extreme heat isn't always helpful. Think about a heavy transport lorry driving over deep ruts. The thin metal body panels shake and vibrate heavily. If you try to weld very thin sheet metal, the intense heat will cause it to warp and bend out of shape. The solution here is riveting. A rivet is a metal pin inserted through holes in the panels, and then physically crushed on one end to lock the sheets together. Because riveting is a cold process, it avoids the heat distortion of welding while standing up brilliantly to high vibrations. Heat is also a problem if you need to join two entirely different metals together, say a soft copper radiator pipe to a hard steel bracket. You can't weld them because they melt at completely different temperatures. Instead, we use a process called brazing. This diagram shows exactly how brazing differs from welding. In brazing, we use a filler metal that melts at a temperature above 450 degrees Celsius, which is much lower than the parts being joined. Only the filler metal melts and flows into the gap. The original copper and steel pipes remain completely solid, keeping their original properties intact. For non-structural joints or joining dissimilar materials, like a plastic cover to metal, engineers rely on molecular bonding. We do this using industrial adhesives, like strong epoxy glues. Adhesives work by using long chains of polymer molecules to chemically grip the surface of the materials. But there is a catch. If the surface has even a thin layer of dust or oil, the adhesive will grip the dirt instead of the metal, causing the joint to fail. The specific properties of your materials, how easily they melt, how thin they are, and how much they flex, dictate which permanent joint is actually the right tool for the job. When we zoom out and look at a fully assembled machine, we are seeing a professional philosophy at work called Design for Assembly, or DFA. This approach relies on two core principles. First, use as few parts as possible to minimize potential failure points. Second, make sure every connection is easy for a human hand or a tool to reach from the exterior. When parts do break in the field, it is usually down to two main culprits. The first is fatigue, where thousands of tiny, repetitive vibrations slowly cause the material to snap over time. The second is bimetallic corrosion. This happens when you join two different metals in a wet environment. A chemical reaction occurs where one metal essentially dissolves to protect the other, causing the joint to rot away. To help you justify your joint selection in exams, we can look at this summary table. If the requirement is high stress and permanence, choose arc welding. For thin sheets facing heavy vibration, choose riveting. If you have dissimilar metals that need structural support, choose bracing. And if the part needs to be maintained, choose nuts and bolts. Engineering is the precision work of matching the physical mechanism of a joint to the specific environment where that product has to survive. Thank you for learning with Yaka Digital Network. For more interactive learning resources, visit us at www.yaka.cc.